Hi, I'm Milo, and I'm going to be talking to you about the compiler writer's perspective on continuation passing style, or CPS. So I think the best way to explain CPS is with an example. So here we have a very small scheme program. You do two multiplications and add the result up. Now, if we convert this into CPS, we get this term. So here, we've encoded the evaluation order, and more crucially, no function actually returns. Every function takes an extra argument, that's the continuation, which represents the entire rest of the program. So we do our first multiplication, bind it to the continuation, our second multiplication, and finally the addition. We conclude with the halt continuation, which is just sort of a marker that the program is over, and maybe if we're in a real programming language, we call back into the runtime, we stop in some way. So getting into this, it's a compiler. We don't want the user to have to write in CPS. We want to transform into our intermediate language automatically. Well, people have tried to do this. So if here we have the identity function applied to the identity function. And right here, we can see that this is a conversion. So we went from 2 different lambda terms to 9 different. This is the Fisher-Reynolds transformation to CPS. Now, the bits in red, those correspond to the lambdas inside of the original program. And the rest is introduced to be 1, valid CPS. But 2, there are a bunch of different bindings here that are what are called administrative redexes. These are things introduced by the transformation. They're artifacts. And quite frankly, they're not very good if we're trying to generate a small, concise, fast term when we're done compiling. Well, people thought about this for a while, and eventually we got to better algorithms like the Don V. Felinsky algorithm, seen here, or the Sabri-Filizin. Well, we want to go further. So these algorithms followed this one rule that you don't touch things in the original term. We're not going to get at redexes that didn't exist before we did the transformation. Well, if you're writing a compiler, you're probably going to follow this up with some inlining, maybe polyvariant flow analysis, all kinds of crazy different optimizations. So we think that this rule doesn't necessarily make sense. So with our transformation, we're going to actually look at a restricted set of reductions that we're going to apply while we transform the term. And this is what we would get from that input. All right, so having given our example, let's go look and change our syntax a little bit. So I'm sorry. So specifying what we actually mean by the reductions. So firstly, we don't want to actually do too much. We want to make our term strictly smaller. We don't want to blow things up. We don't want to make things too complicated. So we're going to only use greedy reductions that will shrink the term every time. Now, these reductions need to terminate, and they should probably always end up in the same thing. So we're going to make reductions that are strongly normalizing and confluent when paired together. Finally, the first 2 algorithms I showed you run in exactly linear time. And we don't want to change this. We want to keep our linear running time even as we add this additional complexity to our algorithm. So what are our reductions? Our no-brainer reductions are 3 different things that we think make good choices for adding to your CPS transformation. Firstly, variables are all the same size. So when you're applying a lambda to a variable, we can inline it. We can get rid of that application. Variables don't, substituting one variable for another doesn't grow the term, so you end up with something that's strictly smaller. Well, we also want to substitute in bigger expressions, but like lambdas or maybe large constants. Now, we can do this, but the problem is if we duplicate them, then our term could explode in size. So we're going to restrict that and say that we're only going to reduce larger expressions, larger lambdas, when they appear exactly once in the body. Finally, we're going to insert eta reduction. So when you have a lambda, which consists of a parameter x, a function f, and f is applied to that parameter only, you can get rid of the outer expression provided that the lambda's parameter is free in f, or that the reference count occurs 0 times. So moving on to our syntax, we're going to use a scheme-like language. We've got here exactly one difference. We're calling our lambdas fun in direct style. And then CPS, we've made a few more changes. Firstly, we want to make sure our grammar is valid CPS. So if you match our grammar, it's a valid CPS term. So here we have 2 types of variables. One for binding user data, that's data that the user wrote, and another for binding continuations. We have 2 types of lambdas, one for, that correspond to procedures that the user wrote, and another that correspond to continuations. Finally, we've got 2 different calls, one that handles user procedures, and again, one that handles the continuations. So with this in mind, we can actually define the Fisher-Reynolds transformation in our syntax. So this transformation takes 2 arguments. The first is a direct style expression, and the second is the concrete syntax of a continuation, which we're going to drop in. So in the variable case, you're going to apply the continuation to the variable. You're going to use the ret form, which is our continuation application. In the case where you have a lambda, you convert the lambda and apply the continuation to it. Finally, the call case, you're going to convert the function, e sub f, bind the result to a parameter x sub f in the continuation. You're building up the continuation. And remember, cont is our continuation lambda. And after you've done that, you'll convert the argument, bind the argument to a new variable, x sub a, and then you actually generate the call syntax with the continuation that you had in the first place when you called f. So once we've got this, we've got a transformation, but it's going to bind a lot of things we don't have to. So in order to do better, we're going to need some new machinery. Well, firstly, 2 of the 3 reductions I've told you about need reference counts. So we're going to have to track them. Secondly, we're going to use environments to perform beta reduction and also to create a term that doesn't have any repeated variable names. So every variable will be unique. This is generally a property you'll want at some point in a compiler, so doing it during the CPS transformation makes sense. Next, we're going to use abstract representations of continuation. So the previous algorithm generates concrete syntax. And this is fine, but it locks you into decisions that aren't necessarily the right ones. If we want to inline things, we're going to need to keep that data around and make the decisions later. Finally, in order to limit our complexity, we're going to split up our top-level function into several smaller ones. And we're going to have 2 different, what we're calling constructor functions. Basically, they're named exactly for one piece of syntax, with their ret and call. And they generate something that is, in our next algorithm, directly equivalent. And in our final algorithm, which will perform the reductions, it'll generate something that is a reduction of the original piece of syntax. So looking at the machinery, here are our environments. We have variables, and we have what we're calling a static closure. The static closure consists of a direct style lambda and an environment. Now, we need to package the environment with it, because once we start performing beta reductions, we don't want to accidentally capture variables or end up in a position where we're doing something that's going to change the semantics. So we need that. The environment itself just maps a direct style variable to either a CPS variable or the static closure. Abstract continuations, well, we've got halt from above. It just maps to itself, variables, and function continuations. Now, the function continuation has all of the information you're going to need to generate this much larger expression from the first algorithm. You're going to have the binding. You're waiting for the function, so that's x sub f. And then you've got the argument expression, which you're going to need to convert. Then you're going to be able to generate the call from the syntax. The argument continuation is just the second part of this. It gives you you're waiting for the argument now. So you've got the function. That's the a term. And then you're going to be able to plot that down into this syntax pattern. Finally, we've got our constructor functions. Here we've got here are the 2 of them. They're notated with capital letters. And the overline function just takes our abstract continuation, or the thing we're putting in the environment, and turns them into concrete syntax. So they map pretty much one-to-one. I think they're fairly self-explanatory. So now that we've got these mechanisms, we can define a new algorithm that's going to use most of these tools, but not actually perform any reductions. In fact, we're going to be exactly like the algorithm we had before, but we're going to use these tools so we can start to motivate where they go and see how things develop. So for starters, the variable case, well, now we're going to perform a lookup. So we've got the old algorithm above, and we've got the new one down below. So you're going to perform a lookup in the environment, and this is going to facilitate beta reduction later, but for now it's just going to generate fresh variable names and make sure we're alpha normal. Well, in the function case, in the new algorithm, we generate a static closure instead of piece of lambda syntax. Finally, for applications, we are going to convert the function, and we're going to build the fcont instead of directly the entire concrete syntax of the continuation. So now that we've got this material, you've already seen our constructor functions, we're going to need our tooling that's going to let us get back to real syntax. So halt, same thing. Variables, same thing. It's the identity function. The function continuation, you're going to generate the cont, wait for the variable that's going to bind your function, and then you're going to transition to having an argument continuation, the acont form, and you're going to convert the argument expression. For argument continuations, well, you've got the function, that's a sub f. You're waiting for the argument, that's x sub a, and you can generate the call syntax. Doing it for values, value variables, direct style variables step to themselves. And then finally, the static closure becomes a lam term. Now you're going to generate a fresh x and a fresh k here. And that's important because you need to do the mapping to swap them out. That's how you get an actually alpha normal term. So now we want to add our reductions into this and get the final transformation, which is going to perform our reductions, generate our beautiful no-brainer normal form. So to get beta reduction, we just have to identify the right places, extend our environment in those places, and have our lookups. You've already seen where the lookup goes, so we just need to figure out what the right places to extend the environment are. For eta reduction, things are a little bit more tricky. See, there's a pattern match, and we need reference counts, but we don't need reference counts from the direct style term. We need reference counts from the term we generate, because our other reductions can accidentally duplicate, or rather intentionally duplicate, the number of variables times a variable is referenced. So we need the count from the term we generate, because once we start performing the other beta reductions, the count we had originally doesn't help us. So with this in mind, we can actually build our new functions. These are the two that perform reductions in our algorithm. So call is a little more complicated now. The variable case, well, you can't beta reduce into a variable, so we have to generate our call form. If we have a static closure, and it's referenced exactly once, then we extend the environment, and we perform the conversion of the body. In the other case, we need to actually generate this concrete syntax for our argument, because it could reduce down to a single variable. And in that case, we want to still do the substitution. If we were to just look at the argument's representation without generating concrete syntax, we might accidentally miss cases. But once we've done this, if it's a variable, we do the extension and extend the environment and convert the body. Otherwise, we're going to generate the call form. Eta reduction, well, variables step to themselves. But when we have eta reduction, we have to convert the body. If the body has that form and the reference count of the parameter in the function is 0, meaning it doesn't appear, meaning we're not accidentally orphaning a variable and taking away its binding, then we can generate the trivial form, just dropping the outer closure. And otherwise, we're going to generate the lambda form for the body. So now we've got ret. This is going to clear away a lot of the underbrush as well. This is going to help us get rid of some of the administrative redexes. Well, if we can't substitute into halt or variables, so we have to generate the ret form. If we have a function continuation, we're going to switch to an argument continuation and convert the function's argument. And then if we have an argument continuation, well, we actually have all three pieces. We have whatever the function is, we have whatever the argument is, and we have the continuation. And with those three pieces of information, we can generate the call, but this is the smarter call. This is the call that might perform inlining. So we're going to be able to do reductions there. There's one form I'm missing, but I don't think it's necessarily helpful for your understanding. You can check the paper where we handle more cases and also explain how to put if into our language. So we proved some theorems about this system. Our reduction system is confluent and strongly normalizing. And our transformation is the no-brainer normal form of the first algorithm I showed you. And we motivate this through the same basic process of defining an algorithm with the infrastructure and then showing that it's a reduction. So what are the takeaways? CPS conversion is compilation. You should treat it like compilation and use it as an opportunity to make a smaller, better, faster term. Compilers are probably going to need a symbol table. So you might as well leverage that technology and that tooling and use it to perform reductions while you're doing the transformation. Fusing passes can help. And even if you're planning to do very complicated flow analyses later or more complicated inlining techniques, having a smaller term to start off with can still make things more efficient for you. Using symbol tables is a good thing. If you're going to have the mechanism, take advantage. Thank you, and I'll take your questions now.